Everyone, welcome to your play posit for the week. We are going to be finishing up that last problem that we were doing in class with that triangle and then having an introduction to parallelograms. So go ahead and grab your notes if you've printed those, or grab your notebook paper and we'll get started. So here's that problem from class. And let me grab my pencil tool here. Because we know that these two sides are equal, we know by that isosceles triangle theorem that the angles across from those sides are also equal. So we can set these two equal to each other. I know in class we use the triangle sum theorem, right? We set it up where all three angles added together equals 180. You can also do it that way, and you'll be factoring at the end of that, which we're going to review a little bit later this year as well. So you should get the same answer. Let's try it this way since we want to use this isosceles triangle theorem. All right, so we're going to get x by itself. Let's first start by combining our x values. Move the 7 over. Get 4x minus 28 equals 4. And then we'll add 28 to both sides. 32. And lastly, divide by 4. So x is 8. So we found our x value, but we want to find the actual angle measures, right? So once you find x, all you have to do is plug it into each of these angles, and we'll get 64 minus 4 is 60 degrees here. And then let's see, 88 minus 28. Also 60 degrees. And let's just double check. This should be 60, right? Since they're the same. Sure enough, 56 plus 4 is 60 degrees. Ooh, what kind of triangle is this? How can we classify this triangle if all the angles are 60 degrees? It is equiangular. If it's equiangular, it's also equilateral, right? All the sides would have to be the same measure as well. All right. Let's move on to our polygon. So a polygon is something you guys have been learning about for literally ever, since you were a baby. So a polygon is a closed shape with straight sides. That's it. I remember teaching my children those basic shapes to start out with, right? Like a triangle and a square and a circle. We're going to talk about all those. So let's see, is number 1 a polygon? What do you think? Remember, at any time, whether or not I have a pause in this video for you guys, you can pause and try things on your own and come back for the answers. That's the beauty of the play posit. Number 1 is a polygon. Yes, there are straight edges. It's an enclosed shape, so we're all good. Number 2, definitely not. We have our curved edges here. 3 is definitely a polygon, straight edges all connected. 4, nope. They are connected, but it's curved. So an oval or an ellipse is not a polygon, and a circle is also not a polygon. And number 5 is not a polygon. It's got straight edges, but it's not a closed shape, closed figure. So this is so fun. I kind of wish we were doing this in live class because it's fun to see which ones you guys remember. So a 3-sided shape is a triangle, right? A 4-sided shape is a quadrilateral. Oftentimes we think of the square, right? But there are other shapes that have 4 sides that are just considered quadrilaterals, rectangle, trapezoid, bunch of different quadrilaterals, right? How about a 5-sided shape? I always think of the building, the Pentagon. A 6-sided shape, that's our hexagon. 7 is, it's either, depends who you ask, but it could be a heptagon, I gotta spell this right, heptagon, or sometimes you see it as septagon. An 8-sided shape, we know that is an octagon, like an octopus. Octagon. 9-sided shape is a nonagon. They're getting kind of funny. A 10-sided shape is a decagon. There we go. An 11-sided shape is a hentagon. Oops. 11 sides. Gotta add that in there. Add that in there, you guys. And the 12-sided shape is a dodecagon. And pretty much after that, I mean, you can look online and you'll find a bunch of resources that give you names for shapes with sides larger than 12. They're nuts. They're interesting and kind of nutty, honestly. Maybe do that. Look up all the sided shapes and tell me which one you think is the silliest. They get kind of crazy. So in this class, we're going to just say an n-gon. So if we're talking about like a 42-sided shape, it would be a 42-gon. So I will never ask you to sort of regurgitate this or put these in a list of any sort, but you'll see them written in questions. It'll say like something, you have a regular octagon, and you're going to need to know, oh, an octagon has 8 sides. Or it'll say, oh, you have a irregular hexagon. Find the angle measure. And so we'll need to know, oh, hexagon has 6 sides. So it's really just remembering how many sides that shape has. We can classify polygons just like we can classify triangles. We can classify polygons in 2 ways. They are either convex or concave. So I'm going to draw some examples of convex polygons and see if you guys can tell me sort of the difference. Let's see. Not a great artist. All right, and here's some concave polygons. It's not a terrible star. This is an example, concave. It's not a true polygon. You can see some curvature here, but this is sort of an example of a concave polygon in nature, if you will. And so hopefully you're seeing the difference here is, convex polygons are pretty regular or traditional looking, and concave have these sort of cavature. That's not a word. Is cavature? It's not. Cavature. They have this sort of opening that should remind you of a cave. They go inward. And so if you can draw a line along the edge of the polygon and it does not intersect the inside points of the polygon, then it's convex. So you can see here if I were to draw a line through this, oh, there we go. It's intersecting the interior of that polygon, so that is concave. Same with the star. Oh, it crosses right through there. It is concave. Any side length that you go along in convex, you will not intersect the interior of the shape, ever. So that's sort of the formal definition. But we can I think we can look at them and say, oh, these are concave. And let's look at some examples. So we're going to say, are they convex or concave? The first one is convex. Right? You can draw that line along any edge and you stay on the exterior or the edges of the polygon. It's convex. This one is I mean, technically concave, but we know this is not a polygon because it has the curvature. So you wouldn't really classify it as concave, but just to kind of show you visually, it does have that inwardness. This one is a concave polygon, right? It's going inwards here. And if you were to draw a line along this edge, for example, these points intersect the interior of the shape. So it's concave. Like you're going to walk into the cave. This is convex, good old triangle there. This is convex along all those edges. And this is concave, right? Anywhere you sort of have an entryway to the inside of the shape. So let's do some more classifying. First, we know what equilateral and equiangular are, right? Equilateral is all the sides are equal. And equiangular, all the angles are equal. So guess what? If a shape is both equilateral and equiangular, we call it regular. Which kind of seems counterintuitive. Maybe it should be called special. I don't know. But if a shape is both equilateral and equiangular, it is called regular. So I like to talk about these mostly because you'll see them in word problems. It'll say something like, you're given a regular octagon. And so you're like, okay, those are my buzzwords. Regular means equilateral and equiangular, and oh, octagon means 8. So you're given clues in the problem that we need to know what those words mean. Get this, you guys, an irregular polygon is something that's just not regular. So it can be equilateral and not equiangular, so it's irregular. So it has to be both of these in order to be regular, and if it's not both of these, then it's just irregular. So basically anything else. What kind of polygons are these? So look at the first one, we can see that all the sides are the same. So this is equilateral, but we only have the 2 pairs of congruent angles, so it's not equiangular. So this is irregular. All right, let's look at this one. We have 2 sides that are the same, 2 angles that are the same. The third side is clearly drawn to be different. So we know that the angles are not going to be the same and the sides are not the same. So it's not equiangular, it's not equilateral. It is a triangle though. You guys remember what kind of triangle has 2 equal sides? That's our isosceles. This is a nice review of classifying that polygon by its angles and sides. All right, the good old stop sign. Show this is a regular polygon. So here's an example where see they're putting this word in here. So we need to know, oh, regular means equiangular, equilateral, both. So they gave us these side lengths. So if in fact this is a regular polygon, these sides must be congruent. So let's see if we can show that to be true. And to do that, let's just set them equal and solve for x. And if we solve for x and we plug it in, and in fact they both are the same, then you have done a little mini proof to show that this is a regular polygon by its sides. Of course, we haven't shown anything about its angles. So we can say, assume equiangular. I should have written that, equiangular. Okay, hold on, I can do better. Ready? Equiangular. There. All right, let's solve this for x. We want to get all the like terms together, right? So I see some squared terms. Let's combine those. Ooh, that's nice. They actually cancel out, which means we're not going to end up having to factor. So I'll bring the x over here. You get 2 equals 2x and divide by 2. x is 1. So let's plug in 1 for x and see what we get. So 1 squared plus 1 plus 2, and 1 squared plus 3 times 1. This is what? 4 and 4. Here we go. They are congruent. This was really meant to be just an example to show you guys how they can throw these words in there, and then we need to know what that word means in order to solve the problem. Central angles. We have seen central angles a little bit with circles, and we're going to see even more central angles when we get to semester 2 with circles. But you can also have central angles in polygons. So here's an example. Here's our central angle, and I bet if you guys were here, you would be able to tell me the definition of a central angle just from this picture. Pretty special. This point is on the center, so it's an angle whose vertex is the center of the circle. Hence the word central. We will have a formula with our central angle. I'm going to pause on that for now because we're not going to use it until semester 2. So, I mean, I can give you a little glimpse if you want. We're going to end up dividing the whole circle by the angle measure. This is the Greek symbol theta, and we measure angles sometimes using theta. But we're going to do a lot more with this in semester 2. All right, let's get to one of our first polygons. It's the parallelogram. You guys, look at this building in Hamburg, Germany. It's a building off of a pier. Isn't that so cool? I think it's so cool. This is an example of a parallelogram in real life, and you can also see some parallel lines and transversals, right? Lots of angles formed. These are windows. So the perspective on this is a little hard to see, but this building is huge. Like, this is a whole, office window there. So tiny people. Like, a person would probably be like this tall, maybe smaller. So it's huge. So a parallelogram is a blank. It's a polygon with both pairs of opposite sides are parallel. That's why it's called a parallelogram. Do you remember what kind of slopes parallel lines have? Parallel lines have the same slope. So we're talking about this side is parallel to this side, and this one is parallel to this one. Both pairs of opposite sides are parallel. So we're just going to reiterate that here on this slide. Parallel. And some examples would be like QR is parallel to PS, right? And QP is parallel to RS. Those opposite pairs of sides are parallel. Both pairs of opposite angles are congruent. Isn't that nice? So Q is congruent to S, and P is congruent to R. Not all 4 of them are congruent. If all 4 of them were congruent, what shape would we have? We would have a square. A square is considered a parallelogram. So think about that. We could ask a question like, it's one of those thinking questions, like can a parallelogram ever have all 4 congruent angles? Yes, it's a square. Consecutive angles are supplementary. Remember, consecutive means one after another. So Q and P are supplementary. They're consecutive. Q and R are consecutive. They're next to each other. R and S, they're next to each other. If you sort of tilt the shape, or they're up and down, if you want to think about it like that. But angles in this shape are either across from each other, right? Or next to each other. So we could say angle Q plus angle R is 180. That's just one example. We could do angle P plus angle Q is 180. That's another pair of consecutive or supplementary angles. And lastly, diagonals bisect each other, but they're not congruent. So we have diagonal here and one here. They're not congruent unless it's a square, right? And they bisect. So that means the pieces are congruent. Bisect means they cut in half into two equal parts. So let's call this point here, let's call it T. And we could say QT, I did not do that on purpose. QT is congruent to TS, I promise. And PT is congruent to TR. So those little pieces are congruent. All right, here's a parallelogram, and it gives us some measurements. EJ is x squared minus 4, and JG is 3x. Find the whole thing. So here's our clue word. It's a parallelogram. It tells us, and we've labeled one of the diagonals. Well, just like we learned and reviewed, we know diagonals of a parallelogram bisect each other. So that means these pieces must be the same. So that's the big clue that's going to help us set up our problem. So we know x squared minus 4 is the same as or equal to 3x. Now when you look at this, you're like, hold on, wait a minute, I have a squared term and an x term. So whenever that happens, we're going to have to factor. So let's get everything on the same side. Actually, just did this problem in office hours today. That's so funny. X squared minus 3x minus 4 equals 0. So we have a trinomial, 3 terms, and it's a quadratic. That's squared variable. Do you guys remember doing these in Algebra 1 last year? I know I covered these in my Algebra 1 class, and we did them for quite a while, maybe at least 3 weeks, if not 4. Factoring is a skill that does take practice for sure. So there are a few ways to factor. Remember, factoring, you're going to end up getting an answer like this. That's kind of the goal. Some people like to guess and check. It means you put an X here and an X here, and you kind of just start picking numbers to see which one works. I'm not one of those people. Some people use this method called slide and divide. It's a method. It kind of seems like a trick to me, so I don't love it and I don't teach it. You're welcome to Google it and look it up on YouTube and watch some videos, and maybe you like it, but it's not something I'm going to teach. If you want to come to office hours, maybe we can play around with it. My favorite method that always works, it's sort of the traditional factoring method. It's called factor by grouping. That's what it's called. And I do use like a little helpful tool. I call it the MA chart. So if you had me last year, you might remember the MA chart. And if not, I'm going to show you right now. So we're going to make a MA chart. M-A. I added a row to my MA chart this year. And so we're going to fill in those top 2 cells, if you will, those boxes from our trinomial. So we're going to do the first times the last. So that's just negative 4x squared. And then grab the middle term. So that's how we fill in those boxes. So we're looking for 2 numbers that multiply. M stands for multiply. A stands for add. Multiply together to give us this one, and add to give us this one. So let's just start listing the factors of negative 4x squared. So you could say like negative 2x times 2x, right? That'll give you negative 4x squared. Also, I mean, it's always a good idea to write them both ways, just in case. And then you could also do like negative 4x times 1x. and negative 1x times 4x. Right? It doesn't really matter which one is negative. You can still get that negative 4. So we need to look at these pairs of numbers to see now which one adds to give us negative 3. Well, negative 2 plus 2, that's 0. That didn't work. 2 minus 2, that's 0. That didn't work. Ooh, negative 4 plus 1, that's negative 3. That worked. You could bring the x's over too if you want. Let's just check this. Negative 1x plus 4x, that gives you a positive 3. It's not that one. So we found the, I guess you could call them magic pair of numbers. These two numbers now we're going to use to replace the middle term. So instead of negative 3, I'm going to write negative 4x plus 1x and just bring everything else down. So I just brought down the x squared and the negative 4. So I didn't do anything fanciful or magical. All I did was instead of writing negative 3, I wrote negative 4 plus 1. That's allowed, right? We're kind of basically going in reverse, if you will. We're factoring. So now we're going to factor by grouping, which means we're going to group the first two terms and we're going to group the second two terms and we're going to see what we can factor out. What do they have in common that we can take out of them, divide out of them? So if you look at these two terms, they both share an x. So I can factor out an x on the outside. When you factor something out, you're dividing each of the terms by whatever that is. So x squared divided by x just gives you x. And 4x divided by x just gives you 4. Right? So you can always check yourself and redistribute. Remember when you have a number or something in front of a parentheses, you distribute. So x times x is x squared. X times negative 4 is negative 4x. All right, let's look and see, what do these two have in common? And at first glance, it doesn't really look like they have anything in common, right? Can't take out a 2, we can't take out an x. So when they don't share anything, you can always divide it by 1. So we'll take out a 1, and you just have what's left, right? Now look, you know it worked when these match. So this is how you write the final answer. X plus 1 and x minus 4. Now we're going to take each of these and solve for x. So you get two little problems, x equals negative 1 and x equals 4. So two possible solutions, which is what we would expect because when you have a squared, it means you're going to have two solutions, up to two solutions. So let's plug those values in to see which one is actually the answer. So if we put a negative 1 in for x, you get 1 minus 4. 1 minus 4 is negative 3. So you get negative 3 here, and then also negative 3 here. So it's good that they're equal because that means we did it right. They should be equal. But can you have a negative length? Can EJ, can the measure of EJ be negative 3? No. No, it cannot. We cannot have negative length. That's why it is not negative 1. So we'll plug in 4. And you get 16 minus 4, which is 12. And 3 times 4, which is 12. Here we go. So EG, the measure of EG is 24. 12 plus 12 is 24. I want to show you guys something on Desmos that may or may not blow your mind. Hold on. I showed my students this last year. If you did not have me last year, your algebra teacher may have shown you this as well. You have access to the Desmos graphing calculator. So I'm going to show you how to use it. I would be remiss if I did not, right? Let me just expand my viewing window here. And we're going to get to the Desmos graphing calculator. I like to do the Virginia version. I don't know why I don't have that like as a favorite, you know? Okay, here we go. Also, my screen is being funny. Okay, so over here, all you do is type the quadratic, type that trinomial, x squared minus 3x plus 4. That was not right. No, minus 4. There we go. Okay, here is the trinomial. We graphed it. If you remember from algebra, you know, solving for x that we got, remember we got -1 and 4? Those are the solutions, right? The solutions are where the graph crosses the x-axis. Check this out. -1 and 4. There's your x values. X is -1 and x is 4. And they are the x values of those coordinate points. Those are the solutions. That's where the graph crosses the x-axis. Most of the time you can use this. I would just caution you because if there are any extraneous solutions, they will not show. But your real solutions, your real values, they're going to show as where the graph crosses that x-axis. So it's really just kind of a good way to double check your work. But that's pretty cool, in my opinion, for what it's worth. All right, let me grab my pencil over here. So our last example, what is the measure of DAB? DAB. So we have some markings here. It looks like a square, but it's obviously not because here this angle is 96 degrees. But remember what these symbols mean. These mean parallel. We've seen just arrows on lines, and then also we've seen like the filled in arrows like are here. So this is a parallelogram. And because it's a parallelogram, we know, one, opposite angles are congruent. So, okay, I'll do that. And remember, consecutive angles, angles that are next to each other, are supplementary. So we can find this angle by doing 180 minus 96. See if I can do that in my head. This is where I get in trouble. So 180 minus 90 is 90. And then minus 6 more is 84, right? Let me double check. Yep. So these angles are 84. We got it. DAB is 84 degrees. DAB. So we used a few things here. The markings, just the markings alone, told us that there were two pairs of parallel sides. So we knew it was a parallelogram. Then our brain said, okay, that means opposite angles are equal and consecutive angles are supplementary. So all of those little steps into problem solving got us to get to that answer. All right, you guys, I will see you in class next week. You won't even believe this, but we only have 2 more weeks of live class in semester 1. So crazy. Thanks for paying attention, and don't forget to watch the play pause it to the very, very end in order for the grade to transfer to the grade book. All right, bye everybody.